Hello and welcome back to the first season of the podcast For Code in Research, the companion podcast for the course on research programming in C++ from the Advanced Research Computing Center at the University College in London. Well, we're getting close to the end of this course on C++ and research software engineering now. Just one more lesson to go after this one. And for this episode, I'm going to continue with the theme about parallel computing and C++. And this time, my guest Marc Hartung from the company Dive in Berlin in Germany, and I will focus on one particular aspect of it, that of programming for a distributed memory system. Talking about parallel computing with C++ has been a bit of a journey of discovery and learning experience for myself, to be honest. As I said in the last episode, I've done plenty of C++ programming before, but not specifically for high-performance computers or HPCs. Fascinating as this world is, there's a lot to take in. In addition to the C++ language and what the standard C++ library offers, there are a lot of extra tools out there, tools you'll need to use if you want to program effectively for parallel computing. One of which Marc and I mentioned last session, the Open Multiprocessing Library or OpenMPI. And in this session we mentioned a few more, and one in particular, OpenMPI. But before I talk to Marc about distributed memory and all that, I wanted to take a step back again and remind us, why parallel? We started talking about parallel computing a little bit more in generic terms. Okay, we went into some specifics like OpenMP, for instance. But the one question that I haven't asked the last week was, under what circumstances or in what situations is parallel computing actually better? And is it always better? Is it always better the more processes you throw at a problem?
General and really sure answer, no, it's not always better. From a developer's perspective, it's always more work. You don't want to program parallel because you have to think more. You have to consider more problems. You have to consider how to get my data from A to B. It's fun for programming parallel, but it's not fun to solve problems. It's necessary to solve problems which need more compute. And as soon as you need more compute, you are better off with parallel computing.
So, in essence, many programming tasks you'll do in future are just happily running on your work or personal computer. But when we think of generating machine learning models, running simulations, like what the company Marc works for does, or other tasks that handle huge amount of data and computations, you're just not getting around doing things in parallel. I had the pleasure of going to the Met Office in Exeter in the UK for a visit recently to think that they could run their climate models or weather prediction services without supercomputers is just unrealistic. In fact, they have 3 of those. And the C++ language is, of course, right in the thick of all of this, which is the reason why this course dedicates a set of episodes to parallel computing. So let's crack on with it. C++ has a model, a memory model, of the underlying hardware that shields you from the complexities of memory units of the machine. Well, up to a certain point. And so, in order to program for HPCs, some basic knowledge of the underlying hardware is necessary to understand how these different multiprocessing and multi-threading tools work and how you can use them effectively in your code. And in the last episode, Marc and I already started talking about how memory is being used. There were 2 approaches, one called shared memory, and the other distributed memory, the main subject for this episode. I thought it might be useful to review again and go through what the differences are. So, to warm us up, Marc and I went briefly through it again, and while doing so, we ended up talking about some of the hardware aspects of modern HPC systems. So here we go. Let's go back to what we started talking about last week, which was to do with memory and memory sharing. So we had shared memory, but we also have distributed memory. And perhaps we can start by define what the differences are between them.
quite simple because it's mostly in the name. Shared memory assumes that multiple processes have access to the same memory region. And all changes to the same memory region are always visible to the other ones. If it's well defined or not, but the changes should be always visible. And distributed computing assumes that each process has its own memory. And to access the memory of another process, you have to do additional work. There needs to be some form of network connection which links them together, or some explicit routines. So it's not physically possible for the process to just get the memory without any more additional work.
Okay. In distributed systems, we really have individual units that handle their own memory, whereas with the shared memory, we have basically a pool. Is that what we're saying?
Yeah. But it's a bit off, but shared memory is always a lie. There's no real shared memory. There's always some form of network protocol which assures something like a change of a chunk of memory happened or not happening. In case of like our laptop or server, it's always the memory controller which connects the cores and handles how changes to the memory, and at least like the main memory, the RAM, happening. So there's also this memory controller is some form of network, like a switch, which takes cache lines in and puts them at places or updates them for several cores. So in a certain scale, it's sometimes better to assume you don't have shared memory as soon as you have more and more cores, because the underlying architecture actually has not real shared memory. That's one fun fact where we come to, I think, later on when we go into mixing MPI and OpenMPI.
So you mentioned the network, because I would imagine then the network solutions being used between shared and distributed, are they different, or is this, I mean, we have, for instance, Ethernet solutions that are linking computers. Is that also something that's working for distributed or shared memories, or are there different kind of solutions available?
When we go to HPC cluster architecture, the network which is used has nothing to do with our home setup, which is Ethernet based. There are more performant versions of Ethernet where you get a lot more bandwidth and a better response time. But usual HPC clusters have specifically designed network and specifically designed network cards, specifically designed switches, which takes a large chunk of the money you invest. Like network is not cheap for HPC clusters. And there are like InfiniBand, which is produced by NVIDIA now. There are some which are created for ARM systems, Slingshot. So there are like some vendors and render products in case of InfiniBand and Slingshot, which enables you to have better performance than what you have at home.
Yeah. So I think the one thing we're forgetting is that when you have large throughput of data, then the speed of the network can be a bottleneck, and which is probably why Ethernet solutions themselves may not be that optimal.
There are also certain features which are not supported by Ethernet. So you don't need to allocate one core which handles the communication. A lot of magic around this, that network card can directly write into RAM. So no core, like direct memory access. And this enables complete different way of programming, which is also fun.
And while we're on the subject of HPC clusters, and we're going to come back to distributed memory in a bit. In the previous section, we talked about cores and probably meaning CPUs, but you mentioned NVIDIA, and NVIDIA is known for producing graphics cards, GPUs, graphics processing units. They've become really like the go-to place when it comes to HPC clusters and parallel computing. Could you give us kind of a high-level reason why that is and what makes them suitable for that?
GPUs, which are the general purpose graphic processing units, is a broader term for graphic cards which can also do computations. And NVIDIA is more or less the one vendor which kicked this off in a large scale to use GPUs for computing. There are several reasons for it. GPUs are made to crunch numbers. They're not made to handle my browser. You could run the logic of Firefox on a GPU, but
Right.
it will be really inefficient. And GPUs are made for processing a lot of data simultaneously as they were made for processing a lot of pixels on your screen to render what you should see. And this is an architectural advantage compared to CPU like ARM or Intel or AMD, where you have a lot of different instructions to enable something like an operating system. And a GPU can just like discard all this and be really efficient just for crunching numbers.
After this little whirlwind tour through HPC hardware, let's take a closer look for just a minute. HPC systems today are mainly clusters, consisting of a large number of individual servers, which can contain a number of CPU processors or cores, but also GPUs. Each one of these servers is called a node. A cluster can contain hundreds or thousands of these nodes or servers. In the show notes, you will find a link to the HP facilities in the UK, one of which is called Archer 2, and when it's complete, it will have nodes in excess of 5,800. And for those of you studying at UCL, where this course runs, there are 2 HPC clusters called Myriad and Kathleen somewhere on the campus. Outside the UK, there are plenty of supercomputing centres. A number of them, and the biggest today, are located in the US. But the EU also has a number of HPC centres, one of which I talked about in another podcast, and it's called LUMI and is based in Finland. Performance in terms of speed of processing is measured in terms of flops. And if you're wondering what that means, it's floating point operations per second. Archer 2, the one that I mentioned just now, has 28 petaflops. That's 28 times 10 to the 15th floating point operations per second. LUMI, which I just mentioned as well, has 340 petaflops. And the supercomputer called El Capitan, which is at the Lawrence Livermore National Laboratory in California in the US, lays claim to over 1,700 petaflops and is said to be the fastest in the world. The nodes within a cluster can be of a single type or indeed different ones depending on the type of supercomputer. For instance, at UCL, the Myriad cluster has high-speed memory nodes, standard compute nodes, and GPU nodes. So, HPC clusters can be huge, but size isn't everything. In a world where we're told that we need bigger and faster supercomputers, it's easy to forget that a large number of applications don't actually need these huge computer centers. They could just as well run happily on small to medium-sized HPC clusters. And it could be better in terms of efficiency if they did run on them. But we'll come back to that a little bit later. For now, let's focus on memory. As Marc said, shared memory is for working with a memory unit on a given node, whereas distributed memory means working with the memory units across different nodes. Distance between processors and memory units matter. And so for shared memory, which sits on the same machine, we can think of accessing the memory in a way that is kind of uniform for the different cores on the node, which is what I mentioned in the last episode called Uniform Memory Access, or UMA. But for distributed systems, we don't have that kind of luxury, and we cannot assume such uniform access across different nodes. Hence, they fall into the NUMA or non-uniform memory access category. And that's even though the network and network switches on and between the nodes are highly optimized. Having said all this, Marc made me giggle when he said that shared memory is a lie. And he has a point, because latency or speed in accessing data from memory is an issue for shared memory or memory on single nodes as well. And I think it's worthwhile looking into this briefly before going on with distributed memory. The basic architecture of a computer today is the so-called von Neumann architecture, named after the Hungarian mathematician and computer scientist John von Neumann. It's also sometimes referred to as the Princeton architecture after the university where von Neumann worked. The main ingredients are what we all know today: a control processing unit or CPU, which holds a control and arithmetic unit as well as a data register. Then we have, of course, the devices for in and output, and finally a memory unit for storing data. All of these components are connected via a so-called systems bus. But here's the rub. Whereas CPU clock speed went up, the transfer rate over the bus made more modest gains. And this divergence has led to a bit of a bottleneck in performance, and it even has a name, the von Neumann bottleneck. Yep, that Hungarian mathematician again. So there are a number of techniques that have been developed to overcome this. That includes, for instance, cache memory, hardware acceleration, and others. In short, making sure that memory access can keep up with processors and process speed has become complex, and in the case of HPC certainly, expensive. And so latency is an issue when it comes to memory handling, both for shared and distributed memory. But, as we said before, they're handled in different ways. We already talked about shared memory during the last episode, so let's take a look at distributed memory now. Let's go back to what the main theme of this episode is distributed memory. You have an architecture where the memory is accessible to a particular processor where something runs on, but you have then multiple of them, which is why it's distributed. So how does the communication then work between all these different memory beds?
It is mostly handled by a library which talks with the network card. That's the basic principle. And you use that by either saying, okay, I want to pass a message on. In a usual internet setup, you would say it's a TCP connection where you say, oh, I want to have a connection with this computer and I want to send it this byte stream. And please push it through my network cable. In HPC, it is much more advanced where you give larger chunks of memory to it and it can process much more data. And you need a sending end and a receiving end, and where like the famous message passing interface comes from, which coordinates how you can get data from one process to another process. But message passing is only one part. There are libraries which gives you a view to all the memory, which is PGAS, which is Partition Global Address Space, where you get the feel of shared memory again in. But every access to this shared memory is something like a specific call. I want to have this memory. It's not like just, I have a pointer, I access it, and I directly have the memory. So underneath, there's also some form of message passing or network communication.
You mentioned a number of there. So it's messaging, and that's what MPI stands for, Message Passing Interface. And we're going to come to one of the libraries, which is called OpenMPI, in a second. But when you pass messages around, isn't there some kind of a performance hit that you experience? I know that you talked about its special hardware, the network switches that are built in, so that they probably take part of that pain away. But is there anything else on top of that that can help to make this more efficient?
The problem in passing messages is waiting for messages to have arrived. So you don't want to wait for your communication. There, asynchronous communication comes into place, where you just initiate the communication, say, I want to send this, or I want to receive something, and then you start computing again and not caring about your communication anymore, and up to the point where you need to be sure that the communication finished, and then you wait for it to finish. And this enables a form of overlapping communication with computation, which is for large scaling problems necessary.
Right. Okay. So because otherwise they would just be bottlenecked completely and waiting for too long.
You leave out possibility to compute. Either your problem is so large that the communication time is so small, but if you scale up, like hard scaling, you take the same problem and just use double the hardware, 10 times the hardware, 100 times the hardware, and see how much faster you get, that your communication time will get larger and larger in proportion to the computation time. And then you need to go over to asynchronous communication. And even then, you need to be sure that your communication does not take longer than your computation. So there's also some form of need to have large problems.
Well, parallel programming does sound like a fine balancing act, doesn't it? And it's true. Because as Mark said, it depends on the size and scale of your problem to decide what solution you go for. So an application with a smaller dataset may well run on a single computer, but there comes a point where you need to go to a bigger machine. And if you scale further, you need to use memory across different nodes of an HPC cluster. And even though the underlying basic calculations may be the same or similar, you will need different programming solutions each time you scale up. And this takes us back to what I said earlier, and as Mark put so eloquently, the need for large enough problems to make efficient use of large-scale computer clusters. So to say it again, not every problem is suitable for a very large HPC. But let's assume for a minute that our computation merits the use of distributed memory programming. As you heard, the key technique used is via communication between nodes. This type of communication is standardized with the so-called Message Passing Interface, or MPI for short. The standard is maintained by a group that is called the MPI Forum, and they are the ones writing the MPI standard. And when I say standard, I essentially mean agreed by consent. That happens in voting rounds for each version of the standard. The forum members come from different vendors, organizations, and institutes. The first version of the standard was released in 1994, and at the time of recording this, we are at version 4.1 of the standard. And the forum is also working on a newer version, currently called version 5.0. With regards to C++, there's an interesting snippet of information. The MPI standard defined a C++ binding with the MPI version 2 standard at the end of the 1990s. But with the version 3 of the MPI standard, this binding was removed again and replaced with a binding in the C language. And so for implementations of the MPI standards like OpenMPI, the only binding you get today to use in C++ is the C programming language binding. And that's something that's been bemoaned by some people, and like the article for which you find the link in the show notes. Before I hand back to Mark and my discussion about OpenMPI and other tools, let's look a little bit deeper what it actually means when we say we pass messages. What, for instance, do we mean with a message? You can think of an MPI message being formed of two parts. In a way, that's kind of similar to sending and receiving a letter through the normal post. You have an envelope with the address of the receiver and the sender, and then, of course, you get the content of the letter inside the envelope. Well, it's some kind of analogy, but MPI has something similar. All processes that are part of a particular parallel computation using MPI get a unique identifier called a rank, which is what you need to provide when you send or receive MPI messages. In other words, who is it for and where does it come from? As for the content of the data you're about to send, you would need to specify the location, that is the start address to where the data are, the amount of data being sent, as well as the type of the data. Apart from these, the standard also allows you to add other arguments, such as, for instance, the tag. Messages are being exchanged with functions. The MPI underscore send and MPI underscore receive, for instance, receive written with capital RECV. Communication can happen from process to process, the so-called point-to-point communication, one process to many processes, or a general broadcast to all processes. MPI is pretty flexible in what it allows you to do, and consequently, the standard is huge. When it comes to the actual implementation of this standard, we already mentioned one solution, OpenMPI, and this is indeed the one people taking the course at UCL will be using. However, it's not the only implementation there is, as you will hear from Mark in the following part of our conversation. Going back to OpenMPI, so we talked about OpenMP, which is something different, but now we're talking about OpenMPI, which is the message passing interface open library. So what does this actually bring to the table?
OpenMPI implements the MPI standard. There's a guideline how to implement such a message passing interface, and OpenMPI is a library you can download, you can use. You can even use it on your laptop and use distributed memory programming on a shared memory system. This way works, not the other way around. And there are also vendor-specific implementations of OpenMPI. So vendors take this source library and adjust it so it works better for their networks. There's also MPitch, which is another implementation of MPI, which is more on every HPC cluster you have either MPitch or OpenMPI implementations.
There is also another another library or another development environment almost, which is NVIDIA's CUDA. And where does this sit in all of this? In this ecosystem of different HPC libraries. So we've got OpenMP, we've got OpenMPI, which implements the MPI standard, we've got OpenPitch, and then we also have NVIDIA CUDA.
Now it's getting complicated because CUDA handles parallel programming for one server, which has GPUs. So you want to compute on GPUs, so you use CUDA. The same you would use OpenMP for shared memory programming the cores of your server. MPI sits on top of this and handles the communication between your servers. So CUDA comes point of you have GPUs, you want to use it, and the implementations of OpenMPI also gives you interfaces to CUDA. So you can directly communicate from your GPU over the network to the other GPU. No need for direct interference of the CPU to get any memory out. That is but only just like one small optimization you would do after doing lots of other stuffs when you wrote your own HPC program. But CUDA in this case is specifically for NVIDIA GPUs, and OpenMP is much more powerful than CUDA because OpenMP has offloading pragmas, offloading primitives, which you can use to also leverage GPU compute. It is newer, just not sure, 10 years old, the standard of OpenMP, which handles GPU computation, but there was a lot of work done so you can use OpenMP code and compile it for GPUs, which is quite cool. So actually, you don't need necessarily CUDA to program.
Well, thanks very much for clarifying that because, you don't want to lock people into one vendor in all of this, even though it's the dominant one at the moment.
Also, AMD on the top 500 list, there are a lot of systems which use AMD GPUs. They're quite powerful too, but they are missing out the ecosystem. So they have to build up libraries. They need to make sure that everyone trusts them, that they will maintain the libraries long enough, and that they are able to fix performance stuff. So AMD is quite new, but there are a lot of systems which uses AMD GPUs. And only one system I know which is large, which uses Intel GPUs. That's also the part.
So one of the alternatives to OpenMPI is called MPitch, and you can look up details from the link in the show notes. And as we heard from Marc, you can also mix OpenAPI with different libraries and APIs, and there are indeed cases when you may want to do this. One of which is mixing OpenMP with OpenMPI, a hybrid parallel programming approach. There's an excellent book on HPC programming that I found that goes a bit more into the detail of hybrid parallel programming. It's called The Introduction to High Performance Computing for Scientists and Engineers and is written by Georg Hager and Gerhard Wellein. And in chapter 11 of the book, they discuss hybrid parallel programming and the basic idea behind it, which is, and I'm quoting, "The basic idea of a hybrid OpenMP MPI programming model is to allow any MPI process to spawn a team of OpenMP threads in the same way as the master thread does in a pure OpenMP program. Thus, inserting OpenMP compiler directives into an existing MPI code is a straightforward way to build a first hybrid parallel program." And then they mention some examples of where that might be useful, for instance, intensive loop constructs. But maybe we're getting a little bit ahead of ourselves, so let's go back to basic OpenMPI. From what I just said, and from my chat with Marc, you may think that OpenMPI would only run on HPC clusters, but that's not true. When you go to the OpenMPI docs page, you'll find that you can install it on your own laptop or personal computer. And that's useful because, after all, it helps to develop and check your program on your machine first before letting it loose on the big beast. OpenMPI explicitly supports Linux and Mac OS X, and I think there are ways in which you can make it run on Windows as well, and you should also be able to build it from source. After all, it's an open source project. When you want to build OpenMPI apps, there are so-called wrappers provided. For instance, the so-called OpenSHMEM, SHMEM, which I believe stands for Symmetric Hierarchical Memory, or the MPI CXX compiler wrapper written MPI C++. Likewise, for launching an application using OpenMPI, you'd use wrappers such as MPI Run or MPI Exec, all in one word. Please take the trouble of going through the OpenMPI docs, also in the show notes, to get you started. There's a lot more to explore when it comes to working with OpenMPI, of course. As I said, the standard and its implementations are massive. Implementing it will take time and experience. So I wanted to find out from Marc how they approach developing programs for either shared or distributed memory. In terms of shared and distributed memory, are there any particular circumstances in which you would prefer to use one over the other? Or is that too bland a question to ask?
I always see the effort to get something running, and then it would be also the plain statement of always start with shared memory, like with OpenMP, in a naive way. So you just start programming, you notice, there's a for loop, I can make it parallel. Or here I can split up the computation and start two tasks. Or I can go through my code and just like put in parallel loops and then start measuring. Can I scale up to 200 cores? Do I have 200 cores? Which hardware do I have? Maybe I only have 4 cores, but I assume I have all compute possibilities that are out there. I would always start with shared memory programming, but don't care too much about it. The common approach is to have shared memory implementations which scale to 40 cores,
Right.
maybe more, but even 16 can be enough. And then you put MPI on top of it. And you combine OpenMP with OpenMPI or with MPIC to scale even up further. But for MPI to work properly, you need a concept for your algorithm to distribute the work. Shared memory can split up the work in really fine-grained manner. For MPI, you have to see, how do I get my 3D space into smaller 3D spaces? What do my processes need to know of each other? And this creates an overhead when you program, overhead in your code, in your readability of your code. And you should only start this when it's really necessary and when you know you need 1,000 cores to get your problem running. Do I have enough main memory, for example? There are not a lot of machines which have beyond 10 terabytes of main memory. So when you go beyond a 10 terabytes problem, at least then latest you should go to MPI.
So in your own work, is that the approach you've been taking as well, shared rather than distributed memory?
We are still in the process of shared memory first or GPU first. Everything else gets quite expensive. And the systems you are getting, we are a cloud computing company. We have access to a lot of HPC cloud hardware. We could use MPI, but we could also use just 8 GPUs on one single node.
Right.
And this reduces the programming overhead. There are multiple developers. There's a lot of development going on, a lot of chaos, a lot of bug fixing. And when we put MPI on top, each feature costs us more. Each customer communication might take more because they are asking about, should I use 20 servers or should I use 100 servers for my problem? And mostly you solve the problem by not throwing more hardware at it. You try to chunk it up in problems. You don't need to simulate always the complete system. You can make it smaller. There are a lot of algorithmic tricks, whether be more cost efficient and more easier to handle, because everything which is highly parallel produces a lot of data. It comes down to looking at it on your computer, and you cannot look at 10 terabytes of data on your computer. So no MPI at our company.
So more is not always better, is what we're saying.
It is always a pain to run really large-scale simulations, because even bug fixing is terrible.
Yeah, I was wondering whether we should open that can of worms, because we haven't really touched in the previous or in this session on how you do actually the bug fixing and how development works in practical terms. How easy or not is it to find problems in environments like that?
There's also one rule of thumb: learn tools earlier than later. For MPI, there are really great tools out there which helps you debugging with user interface. You can coordinate processes on your own. You can create certain patterns in the communication to see, or when does it happen. Or there are libraries which automatically check if your code is valid, your communication is valid. There are tools which help you to find data races or deadlocks when two processes wait for allocated resource while being in charge of deallocating the resource. And there's so many tools, and I would always ask, when I'm in a research institute and you have a large cluster available, the persons who are in charge of consulting you with the cluster and how to develop for it, and ask which tools are directly there to use.
Okay. Well, let's end it there. Thank you very much for your time, Marc. It was great.
Thank you for having me. It was really nice.
Well, that's enough of distributed memory and this episode for now, but we're not completely done just yet, because as you know, there'll be 2 quiz questions. Number 1. Using OpenMPI with your C++ program, how would you get the rank of the process you're running in? And number 2, there is a point-to-point communication between processes, but what if you want to broadcast a message to every process as part of the parallel program? How would you do that? Have fun with the quiz. Next week will be the very last episode of this course, the course on Research Software Engineering with C++ at the University College in London. And for that I invited both Marc Hartung and Klaus Igelberger for a wrap-up, and also to talk a little bit about strategies in parallel computing. And I do hope you'll tune in. You will find the material for this course on the Moodle platform at UCL. This podcast is produced by Peter Schmidt. The music comes from Daniel Lindenblatt in Berlin, Germany. And finally, thank you for listening, and I hope you enjoy the course. And with that, goodbye.